You decide to play either one of the following games, and each game costs €1 to play. In game 1, a spinner with 3 numbers on it, 0, 1 and 2, is spun so that there is a 30% chance that the spinner stops at 0, a 20% chance that the spinner stops at 1, and a 50% chance that the spinner stops at 2. You get back the same amount in euro as the spinner stops at. So if this spinner is spun and the spinner stops at 2, then you get back €2. If it stops at 0, you get €0 back. If it stops at 1, you get €1 back. So this spinner is spun, and the probability that the spinner stops, so the pointer here points at any point on the spinner, is the same. So all points on the circumference of the spinner are equally likely to stop at this pointer. So if that's the case, we want points on this sector, the 2 sector, to stop at the pointer 50% of the time. So we have to make the angle in this sector 50% of 360 degrees, because we want a 50% chance that the spinner stops at 2. 50% of 360 degrees is 180 degrees. Similarly, we want the probability that the spinner stops at 0 to be 30%. So we want this angle here to be 30% of 360 degrees. 30% of 360 degrees is 108 degrees. And of course this angle then is such that the 3 angles add up to 360 degrees. Actually this angle is 72 degrees. So 72 degrees is 20% of 360, because we want there to be a 20% chance that the spinner stops at number 1. Well, we don't have to construct this precisely. I just did it just to illustrate the problem. In game 2, we have a different spinner with 3 numbers on it, 0, 1 and 2. It is spun so that there is a 5% chance that the spinner stops at 0. So we have very similar setup, but we want the probability that this sector here stops at the pointer to be 5%. So basically we want this angle to be 5% of 360 degrees. Now 5% of 360 degrees is 18 degrees. We want there to be a 25% chance that the spinner stops at 2. So we want this angle here to be 25% of 360 degrees, or a quarter of it, which is 90 degrees. And finally, we must have a 70% chance that the spinner stops at 1. So 70% of 360 degrees is actually 252 degrees. So, again with this game, you get back the same amount in euro as the spinner stops at. We want to get the expected amount of money you will get from each game. So remember, it costs €1 to play the game, to play each game. Well, first of all, what I will do is let the random variable x be the number on each spinner. So x1 is the number on the first spinner. So we're going to look at the expected value of x1. So the expected value of x1 is the average of the 3 numbers that appear on this spinner if this spinner is spun many, many times. So we could imagine spinning this spinner maybe 10,000 times. We would have 10,000 values, 0, 1 or 2. We'd sum up those 10,000 values, which come from these 3 numbers, and we would divide by 1,000, and that would give us the expected value. Well, it would give us an approximation for the expected value. So x1 takes on the values 0, 1, 2. So it's a random variable, and there are certain probabilities for each of these values. For 0 the probability is 0.3, for 1 the probability is 0.2, and for 2 the probability is 0.5. To get the expected value of a random variable, as we saw before, we get the sum of the products of each value that x1 can take on times its corresponding probability. So all this notation just means that we're multiplying 0 by 0.3, 1 by 0.2, 2 times 0.5 and summing the results. So just to compare the notation, x1 would be 0 in this case, x2 would be 1, x 3 would be 2. So the small letter stands for specific values that capital letter x1 takes on. And the PIs, well, in this case it's P1, P2, and P3, are the corresponding probabilities. So we're summing from I equals 1 to 3 in this case. But anyway, we don't have to get too much into this notation. All you really have to do is just multiply the values by their corresponding probabilities and sum the results. It's as simple as that. So we get 0 times 0.3, which is 0, plus 1 times 0.2, which is 0.2. 2 times 0.5 is 1. So we have 0.2 plus 1 is 1.2. So again, you have to imagine many spins of this spinner. And imagine noting down all the results. Like the first spin could give a 1. It's like saying x1 takes on the value 1. The second spin could give the value 0. The third spin could give the value 0. The fourth spin could give the value 2. And imagine doing this, say, 10,000 times. Say the 10,000th spin might give the value 1. And then what you do is you divide all of these values by the number of spins, which I think I said was 10,000. And this number would approximately be 1.2. And the more spins we take, say we take 100,000, the closer we will get to 1.2. So that's the idea. So we would say that 1.2 is the expected value for one play of game 1. So if we spin this once, then the expected value will be 1.2. Of course, we're not going to get 1.2 when we spin this spinner. We can only get 0 or 1 or 2, just these three whole numbers. We can't get 1.2, of course. So it's just an average. It's like saying an average family consists of 2.5 children. Anyway, so this is the expected value for one play of game 1, 1.2 euros. But remember, it costs €1 to play the game. So that means that the expected winnings for one play of game 1, the expected winnings are 1.2 minus 1, which is 0.2 euros or 20 cents. Now let's look at game 2. So let x2 be the random variable that takes on the values 0, 1 and 2 with respective probabilities 0.05, 0.7 and 0.25. So I'll write down the values that x2 takes on, and we can see the corresponding probabilities in green. So if we want the expected value of x2, we just multiply each value that x2 takes on by its corresponding probability. So we multiply 0 by 0.05, we multiply 1 by 0.7, and we multiply 2 by 0.25. So if we work this out, we get 0 here, we get 0.7 plus 0.5. That's 1.2. So on average, each spin of spinner 2 will give us the value 1.2. Now what are the expected winnings for game 2? Well, it costs €1 to play the game, so it's 1.2 minus 1, which is 0.2 euros. Explain the meaning of your answers to part 1 and how it might influence which game you would play. Well, it seems that the expected amount of money is the same for each game. Well, it is the same for each game, so it doesn't matter which game you play. What is the probability of not losing money for each game? Well, the probability of not losing money in game 1 is the probability that the pointer is pointing at 1 or 2 when we spin this wheel. If the pointer is spinning at 1, we win €1. So that covers the cost of the game. The game costs €1. If we win €2, we cover the cost of the game and we come out with winnings of 2 minus 1 or €1. But if the spinner points at 0, then we do not win any money. So we've lost €1 in paying for the game. So we don't want this pointer to point at 0. We want it to point at 1 or 2. So we want the probability that x1 equals 1 or that x1 equals 2. So we could use our OR rule for this situation. The pointer is either pointing at 1 or 2. It can't point at both. So these are mutually exclusive events. So we just add the probabilities. We just get the probability x1 equals 1 and add it onto the probability that x2 equals 2. So we have 0.2 plus 0.2, which is 0.5, which is 0.7. We can also see that 70% of this spinner is taken up at these two sectors, 1 and 2. So the probability is 0.7 or 70% that the pointer will be pointing at either sector 1 or sector 2. Of course, another way that we could answer this question is to consider 1 minus the probability that x1 equals 0. So we don't want x1 to equal 0. The three probabilities add up to 1 because either the pointer is pointing at 0 or 1 or 2. So certainly it's going to point to one of these three sectors. So the sum of the probabilities is 1, so we just have 1 minus 0.3, which of course is 0.7. We do a similar thing for this spinner here. For game 2, we want the probability x2 equals 1 or x2 equals 2, so we just add the probabilities of these two events. And if we do that, we get 0.95, or we could work out 1 minus the probability that x2 is 0, or 1 minus 0.05. Next, we're going to get the standard deviation in the returns for each game. Now, you could imagine spinning this spinner many, many times. Imagine spinning it, say, 100 times and noting down the values. The first value might be a 0, the second value might be 2, the third value might be 0, fourth might be 1, and so on. Imagine doing this 100 times. The 100th value might be 2. Imagine getting the mean, and from the mean getting the standard deviation of all of these values. The standard deviation will be an approximation for the value calculated from this formula. This formula involves the probabilities. So imagine 100 values, and of course the more games we play, the more spins of the spinner we take, the closer we get to the exact standard deviation from this formula. So we could imagine doing many more spins, and the more we take, the closer we get to this. Now, little xi stands for a return. Well, I runs from 1 up to n, where n is 3 in this case. So the values of xi in this problem would be 0, 1, and 2. So x1 would be one value. We could call it the first value. x1 might be, say, 0, x2 might be 1, x3 might be 2. X bar is the mean return, which we know is 1.2 euros. Pi is the corresponding probability. So we get the square deviation for each return. Basically, see how far away each return is from the mean return, and square it, and multiply by the corresponding probability. Now, multiplying by the probability is sort of similar to dividing all of this by n for the standard deviation formula applied to a set of data. So dividing by n is sort of the same as weighting each square deviation by its probability. And we sum all of these products, and we take the square root to get the standard deviation. So if I was to write this out formally, we would have x1 minus x bar squared times p1 plus, as far as the last one, which is x2 minus, x3 actually, because we have three values, x3 minus x bar squared times p3. Okay, because n is 3 here, there are 3 returns to consider. So this is what it would look like. And we could, let's say x1 is 0. Let's make that our x1. It looks complicated, but the idea is straightforward. We take each return, see how far away it is from the mean return, which is 1.2, square this deviation, multiply by the corresponding probability. For 0, it's 0.3. Do the same for the next return. This is x2 if you like. Get the deviation of 1 from 1.2, square it, multiply it by its corresponding probability, which is 0.2, and then we have to add on the next square deviation, which is 2 minus 1.2 squared times its probability, which is 0.5. So we sum these products in here and take the square root. Now when you're putting this into your calculator, you can forget about the minus sign in here, because if you square the minus we get a positive result. And 1 minus 1.2 is minus 0.2, but we can just put in 0.2 of course, because we're squaring it, times the probability, which is 0.2. Here we have 2 minus 1.2. That's 0.8 squared. We get 0.76, we get the square root of that number, put it to the power of a half. And to 2 decimal places we get 0.87. For game 2 we do the same thing. We take each return, subtract the mean return. We know that the mean for game 2 is also 1.2. So we can use and start with any value we like, of course. We could take this value. Our x1 would be 1 in this case, if you like, minus the mean value, which is 1.2, we square it. The probability here is 0.7. We could take this as our next value, 0 minus 1.2 squared times probability 0.05. And the next value is 2 minus the mean value 1.2, and probability is 0.25. So we have 1 minus 1.2, that's minus 0.2, where we're squaring it, so we can just put in plus 0.2. Over here we have 1.2 squared times 0.05, and here we have 0.8 squared times 0.25. We get 0.26, put this to the power of a half to get the square root. So to 2 decimal places we get 0.51. So we see that game 1 has the greatest standard deviation in returns. That must mean that we have more of the values 0 and 2 appearing in game 1 than we have for game 2. Because to get the standard deviation in many runs of this spinner, we would get how far these values are from the mean, which is 1.2. So if we have a lot of values that are far from the mean, then this square deviation, we will have a lot of fairly large square deviations, which will in return give us large value for the standard deviation. Whereas here, the values of 0 and 2 crop up less often if we were to look at many runs of this experiment. So the square deviations will be smaller overall. 1 appears much more often, and 1 is a lot closer to 1.2 than 0 or 2 is. So even without doing any calculation, we could sort of guess that the standard deviation for this game is going to be greater than the standard deviation for this game. I forgot to do the second part of question 3. We want to make an argument for a decision to play either game, based on the probability of not losing money for each game. Well, we found that the probability of not losing money for game 1 was 0.7, and for game 2 the probability was 0.95. So we can see that if you don't want to lose money when you play a game, you're better off playing game 2, because the probability of not losing money is greater than for game 1. 0.95 is greater than 0.7. However, if you play game 1, you are more likely to win €2 than if you were to play game 2. The probability of winning €2 on one game of game 1 is 0.5, whereas the probability of winning €2 from one game of game 2 is only 0.25. So it's a case of which do you prefer? Would you rather risk the higher risk of losing money on game 1 in order to have a better chance of getting the top prize, or play it safe with game 2 where you are less likely to lose money? The probability of not losing money is 0.95, which is almost a certainty actually, but the top prize is much lower. Well, the probability of winning it is only a quarter.